Now we move further to Denmark, to Professor Tejs Vegge. I would say very nice combination of theoretical, computational work and experimental work, looking in a holistic view on energy storage materials. If you look at the performance, you find a highly prolific scientist with a very broad scope of work, fuel cells, batteries, many kinds of energy materials covering both theoretical and experimental aspects. Very nice. So, Professor Vegge, the screen is yours.
Thank you very much, Doron, and thank you, Rosie, for the kind invitation and for putting together an amazing program. What I'd like to present today is some of the recent work in my section for atomic scale materials modeling at the Technical University of Denmark, where we are developing computational methods for accelerating the battery discovery. I'll also present the new large-scale research initiative in Europe called Battery 2030+, specifically the project called BigMap, or Battery Interface Genome Materials Acceleration Platform, where we're trying to develop an AI orchestrated discovery platform. But more about that later. So first, to set the scene, I think our previous speaker did that amazingly. If we look at the lithium-ion battery story, it's amazing, but it's also a nearly 20-year discovery process, which we are trying to see if we can somehow fast track by including AI, simulations, and closed-loop discovery. Because the goal is really to leapfrog the traditional sequential battery development, where we know that predictions of a new material has to go past synthesis, characterization, cell and pack level testing and modeling. And each of these can send us one step or multiple steps back. The question is if we can somehow accelerate that process. So the goal of the work that I'll be presenting today and much of the work in Battery 2030+ is really to try and see if we can develop what we call a chemistry neutral approach, but also a versatile approach that allows us to accelerate the discovery process. So this is intended to be applied for lithium-ion batteries, but also for multivalent systems, for other types of batteries that we don't even know about yet. But the key is to develop the infrastructure and an approach that can be adapted to any materials or chemistries we'll encounter in the years to come. So just to set the scene, many of us, and we've seen beautiful examples of that over the last couple of days, are already now integrating theory with experiments, characterization, and testing in design loops. But what we're trying to develop here is really a step forward in that direction and create entirely closed loop infrastructures where we are relying on artificial intelligence, machine learning, as well as the multi-scale modeling and modeling techniques that I'll talk about today. But we're doing it in a closed loop setting together with high throughput characterization, with electrolyte formulations, material synthesis. You can view ourselves as the researcher that can provide input, physical insights, and excellent understanding like the previous speakers have delivered. But the system itself should actually be able to operate in a closed loop, integrating data from all the different domains at the relevant scales, even introducing data from cell level production or performance from end user data. So what I'll primarily focus on here is the modeling side of things. And the key leap in the modeling is really taking it from the descriptive modeling to predictive modeling. And here we are relying quite extensively of some of the groundbreaking work done in heterogeneous catalysis by Professor Nørskov and others, where establishing links between structure and composition of energy materials, specifically catalysts, directly to their functionalities. These so-called descriptors allows you to optimize structure and composition at the goal of improving the functionality. But as we know in the battery community, the amount of different interfaces, the complexity of the reactions that we're talking about, it's very difficult to establish these kinds of descriptors. But this is one of the goals of the kind of research that we're doing. I'll give a couple of examples, and one of the questions to Jeff Dahn, maybe we can shed a little bit of light on the oxyfluorides, the disordered rock salt materials. This is from a recent project called Lithiumrich FCC, where we're trying to develop computational methods that allows us to predict and assess the accessible energy density, also the accessible power density, I'll get back to in a bit, of these disordered materials. So the backbone of the kind of modeling we're doing is electronic structure theory calculations or density functional calculations, but we simply cannot do them for large disordered systems. So what Jin-Yun Chang and colleagues developed was a combination of a cluster expansion method called CLEASE with kinetic Monte Carlo and machine learning that allows us to predict the performance of oxyfluoride materials, in particular the lithium vanadium oxyfluoride materials, predict open circuit voltages, phase transition temperatures, even defect configurations as a function of lithiation, such that we can assess what is the accessible energy density that we can use for repeated cycling. Other aspects that the method also allows us to do is to predict what happens in the mixed transition metal configuration. What is the function of lithiation? How does it influence the capacity, but also in particular the kinetic properties? And the next step in this type of modeling is really trying to establish structure property relationships that allows us to use these much faster accessible energies and structures from the cluster expansion technique, combine it with kinetic Monte Carlo and machine learning to be able to assess the power density or the diffusivity through a macroscopic system as a function of lithiation. And what you see here is the transition from a layered structure into a partly disordered structure. And one of the things that we're trying to establish is trying to understand how can we relate structure and transport kinetics. And this is some work where we were combining the method I just described with machine learning techniques, trying to understand how the local structure surrounding lithium when it moves through the lattice or disordered lattice with the transport barriers. And what we see here, the blue points that you see here, they represent kinetic barriers. And we simply cannot use the traditional energy difference to map out the barriers associated with transport throughout the system. We need to know more detailed, what is the lithium concentration, which cation and anions are present surrounding the jump before we know if a jump is accessible or not. And by using different machine learning techniques, what Peter Jørgensen and others discovered was that simply using the energy differences won't give us a sufficiently accurate description of the transport properties. We need to include specifically the gate cation surrounding the mobile lithium. Once we include those, we can make macroscopic predictions of the transport properties. Another aspect that we're focusing on is the establishment of automated workflows. It's another important step in this AI framework that I'm talking about, developing frameworks that allows us automatically to screen and assess large quantities of different structures. This is actually from a project with our host called eMagic. And what Felix Böhle and Ivano Castelli did was that they prepared an automated workflow that searched the ICSD for structures with a certain magnesium coordination. We could then automatically assess what are the OCVs at high and low state of charge. If those are potentially interesting, we could continue to do a kinetic analysis. And what you see here is the workflow itself, but it's not good for presentation, so I'll move to a structural description of what Felix did. So taking input structures from the ICSD, automatically creating the low and high state of charge structures, assessing the thermodynamic properties. If they are interesting, we can go on to assess the kinetic properties of these magnesium electrode materials and see if they fulfill both the thermodynamic and kinetic properties that we are interested in. An important part in computational screening for kinetic properties is that it is very slow. So in calculating transition state energies is typically an order of magnitude slower than just individual structural relaxations. So we developed a methodology that allows us to accelerate the kinetic assessment. And this is called reflective NEP. It takes into account the reflection symmetries in the system. So this is work done by Nicolai Mathisen and Juan Maria Garcia Lastra, trying to only use the minimum requirement in terms of assessing the kinetic properties. So if the system has reflection symmetry, we simply calculate the energy of the magnesium when it is at the mirror plane. If that is above a certain threshold, we know that that is the lower bound for magnesium diffusion. If that is too high, we discard the material. If it is sufficiently low, we calculated only the symmetric half of the barrier to get a better estimate of the barrier for the transport. If it is completely asymmetric, we calculate the full barrier. This allows us to accelerate the kinetic analysis by a factor of 5. So out of this study for potential candidates to compete with the Chevreul phase, what Felix discovered was a couple of spinel structures that had higher OCVs at both high and low state of charge, a couple of garnet structures that are potentially interesting. And from this kinetic analysis, we saw that, that of the spinel structures, particular 2 candidates had a combination of both higher OCVs and faster transport kinetics. Another important thing, which was also brought up by Professor Jean-Marie Tarascon yesterday, is also the search for, you can say, sort of the unexpected. And this is a workflow for searching for anionic redox processes. And this is work done by Alexander Thyssen and Juan Maria Garcia Lastra, where we use the computational workflow to identify oxygen pairs. So as a function of lithiation, this example is lithium-rich manganese oxide. What we discover is, once we have oxygen pairs, what is the distance between the oxygen pairs? If it's below a certain cutoff, like 1.6 angstrom, we then analyze the magnetic moments, and based on those 2 properties alone, we can determine whether it's a peroxide, molecular oxygen, or superoxide species that we have in the system. You can also see what's lattice oxygen. This is important to know what is the local environment surrounding the cations in the system, but also that we can transfer this methodology to the disordered rock salts that we talked about before, and see that even in those systems, we actually have the onset of anionic redox. To get back to the magnesium ion system, we've also seen that we can analyze potentially interesting electrode materials like vanadium sulfide that we heard about earlier today, which has a high capacity. What is interesting, and this is work done in collaboration with colleagues at KIT and Piotr Jankowski from our group, was also here in vanadium sulfide. We actually see anionic redox processes taking place. So we see the transition of 2 Si2 2- to 4 Si2- species in the system contributing to the capacity. So what we're seeing here is really that we need to be able to assess the unexpected. But all of these are sort of individual materials properties. What we're targeting is full battery discovery and development. And there's one thing we simply cannot get around, and that is interfaces. So a key focus point in the work that we are doing now and will be doing in the future is really related to understanding and predicting the properties of interfaces. So we know that interfaces play critical roles in nearly all battery technologies. So if you take, for example, the formation and evolution of the solid electrolyte interface, we know that it spans many potentially limiting physical mechanisms. So any kind of models that we develop, they need to be able to capture the underlying physics. We simply cannot rely on purely data-driven models that disregard the laws of physics. And this is really a key element in the project called Battery 2030 Plus, which is a large-scale research initiative funded by the European Union, where we are focusing on the very, very fundamental aspects of battery discovery and development. It is headed by Professor Christina Edström from Uppsala University. She sends her regards, by the way. She's very sorry she could not participate here today. But I would recommend that you take a look at our website at battery2030.eu, where you can read more about the Battery 2030 Plus initiative. But like I mentioned in the beginning, there's also a specific project called BigMap that I will be coordinating, and I'll say more about that. But just a few more words about Battery 2030 Plus. What is important is that this is really an initiative that brings together all of Europe in assessing, defining, and developing the tools to accelerate the development of sustainable, ultra-high performing and smart batteries in the future. Here you see the core partners of the flagship umbrella. But what is really important is that we have a number of projects that actually encompass more than 100 partners already. So as of the 1st of September, we have launched 7 different projects. One is a coordination project called the Battery 2030 Plus. And then we have 6 projects that focus on specific aspects of the work that we're doing in Battery 2030 Plus. And I encourage you to go to the website, and there you can also see our roadmap, which outlines what we have identified with the collaboration of leading researchers in industry or through Europe as the main potential bottlenecks and development points for batteries in Europe. But here you see 6 projects that cover different aspects of the core topics in Battery 2030 Plus. Let me just try and illustrate it briefly. Like I said, we're trying to develop a chemistry neutral approach where accelerated discovery is essential, so both materials and interfaces, but also integration of smart functionalities. So out of the projects, we have 3 projects that are dealing specifically with sensing. Those of you that heard Jean-Marie's talk yesterday heard some of the initiatives that we are interested in Battery 2030 Plus there. We have the InstaBat, the SensiBat, and the Spartacus project. And we also have 2 projects on self-healing, so Bat Forever and Hidden. In the periods to come, we will also have cross-cutting activities related specifically to the inclusion of manufacturability and recyclability in the discovery process. But from now on, I'll focus on the BigMap project. So BigMap also brings together a large quantity of academic institutions, large-scale research facilities, research organizations, and industry. So industry spanning materials and even cell production in Europe. And what we're trying to do together is really reinvent the way we invent batteries. So trying to develop a new infrastructure, sort of a holistic infrastructure, like Doran said in the beginning, where we're trying to implement artificial intelligence and machine learning in critical aspects of the discovery cycle. So really have an AI orchestrated battery discovery process. So I'll spend a little time on this slide that was also on the first slide I presented today, where you see 8 pillars of traditional research, more or less, in the battery community. Whether you're doing modeling, like I presented in the beginning, operando characterization, synthesis, manufacturing, or testing. But what you see in this plot is a flow of information or flow of data that goes both ways from all domains into this AI orchestrated discovery. And I think this is an essential part in the framework that we're trying to develop, is that data can be acquisitioned, analyzed, and utilized from all the different domains at any given time, and utilizing the data when it is most relevant for the discovery process. So let me give you one brief example. So we can take a structure, either from our previous presenters, titanium sulfide, or a material predicted from simulation. We can then go in and use that information about the stoichiometry and the structures from the prediction and actually launch a synthesis directly, controlled by the AI. We can then automatically characterize that material if it turns out, and that characterization can be done using machine learning modules that automatically assesses whether or not we actually have the phase that we were interested in. If that's not the case, we can automatically launch a supporting simulation that can then identify what is the origin of this phase transition. Is it because we're too high in terms of lithium content? We can then continue the characterization with cell level testing while we launch the second simulation or the second synthesis procedure, such that it is not a sequential process anymore. We can continuously update the materials on the fly. A central aspect here is really the ability to bridge spatial and temporal scales in battery discovery. So we're ultimately trying to bridge from the scale of electron transfer mechanisms all the way to the durability of commercial batteries. So this cannot be done with any traditional scale bridging method. Actually, we have to leapfrog several methods in order to be able to achieve anything remotely corresponding to that kind of an ambition. But let me give you a couple of illustrations of how we're viewing this complex challenge. And again, I'll start with the simulations as an example. So what you see here is ab initio MD simulations. So this is more or less state of the art of what we can do to describe solid liquid interfaces. And what we see here in work done by Henrik Christoffersen and colleagues is that the inclusion of an explicit description of the electrolyte actually changes the property of the adsorbed species on the surface of the electrode. That gives us a large training set, but it also encounters another problem, and this is one thing that even though we're using state-of-the-art density functional calculations, we know that there are certain chemical bonds that are not described well, even at this level of theory. So the making and breaking of carbon-oxygen bonds, for instance. But there we can rely on machine learning techniques. This is work done by Rune Christensen and others, where we can automatically identify what is the origin of any intrinsic errors in the calculations. We can then correct for those such that we can train cheaper machine learning models, neural network potentials, that allows us to describe much longer time and length scales of this solid electrolyte interface. Let's say we want to study the SEI formation. We can get to much longer time and length scales in that analysis. But the sort of mental quantum leap here is that we're not trying solely to do this in the simulational realm. So we're not trying solely to find a way to bridge density functional simulations all the way to finite element. We're also not trying to develop an infrastructure that allows us automatically to launch simulations to support spectroscopic analysis or electrochemical testing done. We're actually trying to develop a holistic infrastructure that allows us to go to any domain at any relevant scale to acquisition the most valuable data at any time to figure out or to identify what is the critical descriptor for bridging certain scales. What is the parameter that we need to know? Sometimes it can be going from simulations to experiments, and other times it can be vice versa. So the kind of workflows that I showed you in the beginning for just simulations, you should view the workflows that we're trying to develop here as integrating both simulations and experiments and even testing. So this integrated workflow that I showed you here, the top part reflects more or less what I illustrated for the magnesium electrode, but we can also use the simulations to derive new experimental parameters. Let's say that we actually need to change the synthesis properties, or for combined experimental and computational characterization of a new phase that emerges, we can go in and systematically exchange data across the different domains and thus accelerate the discovery process of the target materials that we are aiming for. So we're really trying to do ultimately inverse design. So start from the properties that we're interested in and back calculate to the original materials and treatments that we have to apply. A key element in this is data, and I won't go into how much data we need, but we need quantities of data that are way beyond what any individual group can deliver. And another important aspect is that this data has to be fair. So we have to be able to find it, access it, and reuse it, and that's really a key challenge. So developing a common data infrastructure poses one of the biggest challenges in the BigMap project. Fortunately, we can rely on some of the work that has been done primarily in the computational realm, headed by Nicola Mazzari and his groups at EPFL and the Marvel projects also, and in the so-called Materials Cloud project. So what is done here is trying to develop a shared infrastructure that allows you to use different codes, and now hopefully also soon different experimental techniques, but share data across the different domains and be able in a much faster way to launch these integrated workflows. So you can go in and use, let's say you're doing an experiment, you can actually go in and automatically launch the simulation that you need for interpreting the experiment. So data, we need it, and we need it from the experimental domain also. So those of you that heard Professor Martin Winter's talk yesterday knows that at MEET they have a unique system for electrolyte formulation. And they're actually doing one thing that's essential for the BigMap project, which is also done in the computational realm, is that they are ensuring data provenance and data lineage, such that we can go back and see the origin of the data, because the quality of data or fidelity of data is an essential aspect in the kind of models that we're trying to develop in BigMap. And I'll get back to that in a little bit. But developing high throughput screening systems where you, for instance, laser imprint QR codes, so you know exactly what the composition or the formulation of your electrolyte is. You also know exactly what experimental condition a given experiment was conducted under. That is the kind of information that is needed if we're going to develop this infrastructure. So another important aspect in terms of gathering sufficient data is utilizing the large-scale research facilities, in particular developing multimodal characterization techniques and autonomous characterization techniques, so integrating both high-fidelity data, so coming from large-scale facilities, with high-throughput data from our large-scale facilities. Ultimately developing multimodal characterization techniques, so if we're studying the formation of interfaces, we could, for instance, combine a spectroscopic, a structural, and an imaging technique that would then automatically be able to launch the corresponding simulation to enhance the interpretation and the understanding of the material. Here we can rely on work done within our own consortium, but also excellent work being done at Berkeley and Kirsten Person's group, at Caltech by John Gregoire and others, developing machine learning-based modules that allows us to do an autonomous on-the-fly analysis of the spectra generated such that we can predict in a systematic and useful way. A key element for, you can say, for the success of the models that we are trying to develop here is that we are able to quantify when the most valuable data comes from experiments, come from simulations, and at which scale we want to perform the simulation or the experiment. So we know if you're interested in SEI formation, the onset of SEI formation, we could, for instance, use advanced spectroscopic techniques, couple them with the kind of ab initio MD simulations that I just showed you. But we know if we're interested in studying crack formation or aging, those techniques will be completely irrelevant because we cannot access the relevant time and length scales. So being able to create cost to value or cost to fidelity functions for the different techniques such that we know where to acquisition the most pertinent data at any given time is essential. Once we have this data, what we're trying to do is to develop what we call dynamic interface descriptors. So we go back to my second slide, finding these meta parameters that link the structure and composition of a material, an electrolyte, or an interface directly to its properties. And one of the things that we're trying to do here is to develop deep learning models that allows us to encode the properties from molecular materials and microstructural space into a latent space where we can identify these dynamic descriptors. We can then optimize in that latent space and decode back into the physical world, into molecular space, material space. So let's say we identify what is a suitable or relevant additive, what is the preferred facet of our electrode if we want to create the SEI that has the best performance for given chemistry. Another important aspect in the kind of models that we are developing is uncertainty, because we have a number of different uncertainties. So I talked about fidelity. So for a certain simulation, we can go to different levels of fidelity. So classical, quantum, depending on the accuracy needed to describe a certain phenomenon or a certain parameter. But we really need our models that predict the spatial temporal evolution of the interfaces to be, you can say, a combination of physics aware. They need to abide by the laws of physics, but they also need to be able to be uncertainty aware. So they need to know when they don't know, not necessarily what they don't know, but when they don't know. And then they can go and acquisition data, either experimental data, computational data at the relevant scale to limit that uncertainty, to improve the prediction. And then we can make time series or Markov state models that allows us to describe the spatial temporal evolution of the battery interface. Ultimately, then reversing those to give us inverse design capabilities. So the last two short topics I want to talk about is synthesis. So ultimately, we want to be able to do autonomous synthesis controlled by the central AI, but we know that that is very difficult to do in the inorganic synthesis procedures. So we'll start out by doing it for electrolyte formulation, trying to use synthesis robots to optimize the electrolyte formulation to get the properties that we want. There are a number of beautiful examples out there, the synthesis machine and the computer, for instance, but we can also use artificial intelligence to guide us in terms of, let's say, searching for cobalt-free, nickel-rich electrode materials by looking at the synthesizability of similar compounds in phase space. So we get ideas about how synthesizable a certain material is before we launch the synthesis. The last example that I wanted to bring up is just that ultimately in time, in battery 2030 plus, using the BigMap infrastructure, we also want to include direct input from advanced sensing, like you've heard about, the self-healing additives. So let's imagine that you have a spatial temporal model that can predict a failure mode to happen. We can then automatically launch a preemptive self-healing from the self-healing additives in the electrolyte. Another aspect is also predicting for a new chemistry, what are the right manufacturing techniques? We heard also the talk about calendaring. What is actually needed for this electrode to be sufficiently ductile, so forth. Finally, the integration of production and recyclability directly into the discovery process. So with these examples, I would just like to conclude and give you some of our perspectives. We were really seeing a move from the sequential Edisonian battery development to autonomous discovery of battery materials and interfaces. I gave you one example, our proposed BigMap structure, the project that just started and we hope will run for 10 years. But the core concept is really integrating data from all the relevant domain and using artificial intelligence and machine learning to orchestrate the data acquisition and analysis such that we are able to make predictive models that can help us to suggest new materials and interfaces. The central aspect in this is these closed loop discovery workflows where we bridge simulations and experiments relying to a very large degree on uncertainty quantification. And then finally, to include self-healing, advanced sensoring directly into the discovery process. And with that, I would just like to thank the people who contributed to the work I presented here. I'll try to mention most of them during the talk, but in particular, I'd like to thank the BigMap Consortium and the Battery 2030 Plus Consortium and the European Union and all our other funding agencies and you for your attention.
Well, thank you very much, Professor Vegge, for the intriguing talk. It deserves some discussion. To what extent we can really lean on, let's say, machine learning in the case of batteries. This field is multi-parameter field with a lot of issues when 10 ppm of garbage can change the whole picture. So I would say there's no replacement to step-by-step, very systematic experimental work in which we turn any stone on the way. So we have to work together, but you do it in fact. You do this experimental and theoretical work in parallel, so you are in the business.
I fully agree that it's essential, and I would actually say that one of the core things in what we're trying to do here is really to derive the physics. What is, we call it the battery interface genome, but what is really the underlying physical mechanisms at play? What is it that, for instance, determine dissolution from the positive electrodes? What is it that determines the formation of the SEI? But it's only once we have that we can make the advanced models that can allow us to predict the new materials. So the physical understanding is essential.
So I want to add a comment. We see here a very nice evolution in the talk this afternoon, the evolutionary process of a good battery development, starting from the very systematic work of Sten on the systems. And then before, we heard Jeff Dunn on the very systematic work on specific materials. And based on, let's say, very systematic work coming from different directions, and based on very solid experimental work, now you can go further and take the field further by good computational work, which is nice. And I give you all credentials with this, let's say, machine learning based on the good experimental work that we have. I see that there are some questions, if you don't mind. You can see them also. There is a question. At what threshold are you discarding? How did you define the cutoff? One of the questions that I have in front of me.
That's a good question. So I'll try to go back to the slide just to illustrate it. So that cutoff can be set arbitrarily. So we set it very conservatively because we really don't want to discard candidate materials that are potentially relevant. But if you have a kinetic barrier in excess of 2 eV, we know it's dead in the water. It will never be commercially relevant if the transport of magnesium is in excess of 2 eV. So you see here we have candidate materials in that actually have kinetic barriers in excess of more than 1 electron volt, which is also the case almost for the Chevreul phase. So we tried to do it conservatively because we actually ended up having only a few candidates that had high OCVs at both high and low state of charge, and also interesting kinetic properties. So we try to be conservative when we do this. And I see a second example, and that was actually a slide that I cut. So Alok Mani Tripathi was asking whether machine learning can be used in cycle life assessment. I think there's a beautiful example, some work done Will Chu at Stanford and collaborators on actually trying to predict the cycle life of commercial cells, and using also machine learning techniques similar to some of the ones that we are discussing here to develop fast charging strategies that actually improves the durability of the cells. So instead of inventing new materials, actually taking the materials that are there and getting the most out of them. So like we heard Jeff Dahn mention in the beginning, be careful if you go above a certain charging voltage, above a certain capacity. Those kind of things, these machine learning models can also learn. And it's actually low-hanging fruit.
Maybe we have time to go maybe through two short questions more. I see a question: can machine learning be used in life cycle assessment of and thermal heat generation of a particular cathode material cell? Well,
I think I answered the first part of it. I think for the second part, we would have to look at the specific electrode. But there are a couple of examples. I also showed a few here where you can say not so much the thermal heat generation, but oxygen evolution, for instance, which was also mentioned by the previous speakers. Those approaches can allow us to detect the onset of oxygen evolution as a function of lithiation, for instance. Similarly, for the thermodynamic heat release, we can also do that. But it depends a little on the complexity of the material. If you have a highly disordered material, it gets much more complicated.
Very good. I see here another intriguing question. Can you give an example of a real case in which automated discovery has helped, or what is machine learning, or have helped to advance the battery research? Maybe the theme of the question is if you have already living examples where machine learning lead to new materials, like new progress in the field beyond what we reach by systematic experimental work.
It's a very good question, and I would say that the best examples are actually from organic flow batteries. So we take Alanis Burgutzik and the work done with Mike Assis and Roy Gordon at Harvard. We also have a project with them looking at organic redox flow batteries, because there a number of good organic redox molecules have been identified, and in particular identifying materials that are also more stable, so stable against degradation mechanisms. And the reason that is the best example I can bring up is that a lot of these methodologies were actually developed for molecular and chemical species, so chemical space. So in the pharmaceutical industry, some of these technologies have been applied before. And that's also why we start with the electrolyte and the electrolyte formulation as our primary target. So that would be the best examples that we have there.
Very good. In fact, there is another interesting question, but maybe we'll try to push it, although we have to move forward. But someone is wondering, Jonathan Horowitz is wondering, how do you account in artificial intelligence and this machine learning and this automated studies for the candidate materials stability, bulk versus interface, and their applied potentials?
So it's a very good question. I would say, in particular, the second question, there is no way I can answer that in this short time here. So I'll try to answer that one in writing. But for the first, we know that as a function of potential, we have different coverages. I only showed you a couple of relevant coverages on that specific electrode-electrolyte interface. So we can model, and also here compare to experiments, such that we know that we are actually modeling the electrode at the relevant potentials. So what you saw in the example that I gave with the Ab initio MD was actually not a process involving lithiation or delithiation. It was just an adsorbate interaction with from the electrode to the electrolyte. But the second one, I would recommend a written answer.
Now I have to say that if you have really pure materials, then you can also account for what happens on the interface, because there is thermodynamics which take place, and many things can be predictable. The thing is that we don't have really clean materials, and as I said, every few ppm of garbage can change the whole picture. Well, very nice. Thank you very much for this beautiful talk, and intriguing, inspiring, and now